What we would like to build is a procedure for reducing a system of equations to as simple a form as possible, ideally, finding the unique solution of a system if it exists. We'll start by informally describing the procedure and using it to solve some example systems of equations. Then we'll explore some special cases that can occur during the algorithm. Once we have a better intuition about the algorithm, then we'll begin to write code which will define the algorithm's precise operation. The algorithm we will discuss is a classic algorithm called Gaussian elimination. Though it is named after the 19th century German mathematician Karl Gauss, the algorithm was known to the Chinese as early as the 2nd century BCE. The basic idea of Gaussian elimination is to gradually clear variables in successive equations. So the first equation will have all the variables x, y, and z. Then the next equation will end up with just y and z. And then the last equation will just have z. That way, the last equation just becomes z equals some number, and then since the second equation only has y and z, and we know the value of z, this allows us to find the value of y. Finally, we use the values of y and z in the first equation to find the value of x, giving us the solution, presuming there is a unique solution after all. We can do this by adding or subtracting appropriate amounts of an equation from all equations underneath. Let's look at this example system. X minus 3y plus z equals 4, negative 3x plus 9y plus z equals 0, and y minus z equals 1. In order to clear the x term from the second equation, we can add 3 times the first equation to the second. Remember that adding or subtracting multiples of equations is a valid operation. This transforms the second equation into 4z equals 12. Now we could go ahead and use the second equation to find the value of z, but for now we're going to ignore the shortcut and show how the procedure works in general. Like we did before with the x term in the first equation, we want there to be a y term in the second equation so that we can use it to clear y terms below the second equation. That way we have successive loss of variables. If, like in this case, there is no y term in the second equation, we look to below the second equation for one with a y term. Then we can swap the second equation for the equation with the y term. In this case, we'll swap equations 2 and 3 to get a y term in the second row. Again, this is one of our valid equation operations. Now the second equation is y minus z equals 1, and the third equation is 4z equals 12. We have no y terms underneath the second equation, so there are no more terms to clear. Finally, since we're at the bottom equation, there are no terms underneath the z term in the third equation. Notice that our system of equations is in a special form. Each variable that appears as a leading term doesn't appear in any further equations. This form is sometimes given a special name, such as triangular form or row echelon form. In this lesson, we will call it triangular form. However, this system does not represent the same set of planes as the system we started with. By adding and subtracting equations, we do change the planes involved. However, we have changed them in such a way that the common intersections of the planes remains the same. Once we've reached triangular form, our next task is to clear upwards, so that way we isolate each variable in its own equation. First, we're going to solve for z in the bottom equation by multiplying it through by 1/4. Notice that this is the third equation operation we had defined earlier. This gives us the bottom equation now reading z equals 3. To clear upwards, we can add the third equation to the second equation. This makes the second equation become y equals 4. Then, subtracting the third equation from the first equation gives us x minus 3y equals 1. Notice that z is now in its own column. Now let's focus on y. We've already solved for y equals 4, so the last step is to clear upwards so that y is also in its own column. To do this, we add 3 times the second equation to the first, which makes the first equation become x equals 13. Using just the 3 operations we spelled out earlier, we have found the sole point of intersection of the 3 planes described in the original system of equations. Note that we can check that the point 13, 4, 3 satisfies all three equations in the original system. I'd like to run through this set of operations one more time, but this time including a plot of the three planes that these equations represent. That way you can see visually what Gaussian elimination is doing. One thing to keep in mind is that the common intersection of the planes defined by these three equations should never change during our operations that we use. After the first operation, notice that the green plane has rotated along its intersection line with the red plane and is now entirely horizontal. The second operation, which swaps two equations, just changes the color of two of the planes. The third operation, which multiplies equation 3 by 1/4, doesn't change the blue plane at all. By adding the third equation to the second equation and isolating the y variable, the green plane, which is y equals 4, is now perfectly orthogonal to the y-axis. Next, clearing the z variable from the first equation means that the red plane no longer has any dependency on the z variable. Finally, eliminating the y variable from the first equation makes the red plane perfectly orthogonal to the x-axis, and now the meeting point of the three planes is easily identifiable.